Yes, this is a hopefully a quick-ish introduction into normal distribution, just to give you an overview, tell you what it's about, and hopefully a tiny bit of understanding of what it's all about. So a normal distribution is usually used for firstly measuring continuous data. So it's basically for situations that can take any particular value. The most common kind of use for normal distribution are things that are naturally occurring. So things like heights of people, weights of different things, or errors in scientific measurements. And there's a few others, IQ, scores in exams, things like that generally are modeled using some kind of normal distribution. There are a few nice things to do with the normal distribution. And the very first thing that I'm going to talk about is what's it look like. So the normal distribution itself, if I just draw it, has what we call a bell curve. So it starts down here, it comes up, back down, and then peters back off. It shouldn't have that little flicky bit at the end there, but that should look something like that. The very central part here, this is where the mean occurs. So obviously along the bottom, this is a scale. Usually, let's just call it height for now. So let's just get used to that. So if I call that the height, this bit here right in the middle, that is the mean, and this will be perfectly symmetrical for the kind of standard normal distribution, which we'll be looking at. And then it's just looking at parts from there. So this is known as being symmetrical. So not only is it the mean, it's also the median, it's also the mode. So when we standardize our information, when we look at this natural data, what we'll find is this middle section here. When we've got enough data, this will be the mean, it'll be the mode, it'll be the median. A little bit about talking about how to measure this. So we've done binomial before. This time we take our x, our CRV, or continuous random variable, and it's going to be modeled normally. And the bracket this time, the two parameters we use is the mean, and we also use the variance, which is the standard deviation squared. And it's often written like this to remind you that this is standard deviation squared, which is the population variance, and this is the population mean. So it's really important that, that you understand how to actually write this. So I'm going to steal the example that I've already got from kind of like the book. So if you imagine height, for example, and if you wanted to, let's say, model kind of the height of some adult males in a particular city, and we knew that their mean was 175 centimeters, that would go right in the center here. So that would be 175. Height would be measured in centimeters. And let's say they had a standard deviation of 12. Well, the way that we'd write that model is X is modeled normally with a mean of 175 and a variance here, it's going to be 12 squared. So we can pick out here that that's the mean and that's the variance. So what in the world does this actually mean? What's this variance about? Well, firstly, let me just go on to say the area underneath this curve. So the entire area, this accounts for the entire population. So when we add up everything here, the area under this curve is equal to 1 because these are all probabilities. So if let's say I wanted to know what the probability of X being less than or equal to 175 or 1.75, that is all of this section on the left of this point. So it's every single person. Now, keep in mind, if this is the mean, the mode, the median right in the middle, then that should add up to half the population, or 0.5 as a probability. If I want everyone, so any height that you can think of from 0 height all the way up to 1,000,000 centimeters, obviously this is an asymptote, so it will go on forever. The probability is literally becomes 0 as you get further and further away though. But that will add up to 1. So if I want the height of everyone, then it would equal to 1. So that is the area under the curve. So when we talk about the area under the curve, that's actually the probabilities of certain things happening. Now let's talk about this variance or this standard deviation. If we add the standard deviation to this, that's 12, we get 187. So let's just put that in about here. So we've got 187. And let's take it away from here just to go the other way as well. So taking away 12 from here would give me 163, and that's going to be symmetrical again. So let's just, oh, my curve's not kind of entirely symmetrical. Let me just put this more central, let's say. Let's just put that like there-ish instead. And then that can go about there. Okay, that is best I'm going to get. So that's 163. So what I'm saying here is we've got the mean and we've gone one above it, or a standard deviation to the right. We've also gone a standard deviation to the left. So what's special about this? Well, within this kind of range, so between the standard deviation being kind of added to the mean and taken away, so the mean minus standard deviation up to, let's just call that x right there, the mean plus the standard deviation. Well, the probability of this actually being the case is equal to around 68%. And it's always, so about 0.68. So that kind of percentage of being in there is about 0.68. And that's quite important. You need to remember that particular number. So we've got 68. The next one is, what about if we go 2 away? So what about the probability of being mu minus 2 standard deviation and mu plus that 2 standard deviation? So for that, I just want to add 2 again. Not 2, sorry, 12. So we get 198. And now we're looking really tall. I'm taking 12 from here. We're going to get 151. So at this point, you can see we've got all of this area. So if you imagine all of this shaded now, what's the probability of being within 2 standard deviations of the mean? Well, again, for normally distributed information, for normally distributed data, this is around 95%. So 95, so this is 68%. That's still quite high. It's more than 50% of people. This is 95% within 2 standard deviations of the mean. And finally, within 3 standard deviations of the mean. I'm not going to write, actually, I'm going to have to just to stick with it. But within 3 standard deviations of the mean, I'm not going to put the numbers on here. It's actually really, really surprising. This is going to be 99.7% or 0.997. So at that point, you've got a lot, if not all, pretty much all of the important bits you need. So we've got some extreme outliers there. In ours here, it'd be 210 centimeters and all the way down to 139. But you can see that's going to take us right down to this tail. So like 139's here. And when we shade, 210's all the way up here. So when we shade this, it's literally everything apart from these tiny, tiny little bits. And those tiny little bits will account for 0.3% of the data. You can imagine, obviously, if we've got a large number of data, we can work out how many that is around. So that's how the normal distribution works. It's got this bell curve. So just to recap, firstly, it's got parameters mu and variance. So they're the population mean and population variance. It's symmetrical. So the mean takes place right in the center, which also happens to be the mode and the median. It's got this bell-shaped curve, and they have asymptotes at each end, as you can see. The total area under the curve is equal to 1. And I think that's pretty much all of the important bits we need to talk about for now. One important thing to do is, which I'll talk about shortly, is if you're trying to, on your calculator, when we're trying to use or input things and you want to basically rule out anything below the mean to try and get it basically down to 0. So if you want basically to get a lower bound or an upper bound as close to 0, basically anything outside of 5 standard deviations is about the rule of thumb. That will be way out of our data range. So that's going to be the big thing that we're looking for. And I'll talk about that in a second when we bring a calculator to do these. So apologies for that. Let's just get this up and running. So here we've got the diameters of a river produced by a particular machine is modeled normally with mean 8 and variance 0.2 squared, or standard deviation 0.2. Find P of X greater than 8. And all we're going to do here is, I'm not going to use my calculator. I will show you this on the calculator in a second, but I want to talk about where kind of this comes from. So in this particular one, let's just imagine what this would look like. So I'm going to draw this. So we've got our bell curve. It's a terrible bell curve. Let's do that again. Better if If I could draw straight lines to start with, to be fair. That'll do. So we've got a bell curve, and right in the middle here, we know that this is 8 because it comes from here. So let's just put this up here. Mean is 8 and standard deviation is 0.2. If I add 0.2 to that, then this will take us to 8.2. And if I take away 0.2 from the mean, I get 7.8. You'll notice that that's really important for part 2. But to start with, I'm just going to do some coloring. So to be greater than 8, it's everything above 8. So it's this section here that I'm just coloring in. All of this bit here. So what's the probability of that? Well, hopefully you remember from before, I said, even though, because the mean's in the middle, the area under the curve adds up to 1, and we shaded exactly a half. So the probability of that is just 0.5. I'm going to confirm this in the calculator in just a second, but that's going to be part A. So the probability of X being greater than 8 is 0.5. Part B, the probability that it's between 7.8 and 8.2. So that's this bit that I'm now shading. And again, hopefully you remember that that's now between 1 standard deviation. So if we look up here, we've got 0.68. So this bit's just getting us used to these special values. So just be on the lookout for these. You can use your calculator to double check these though. So we got 0.68. So using the calculator, we go menu, and we want to get into the stats mode. So the stats, if we just go to number 6. 6 is stats, actually. We don't want stats. We want distribution, sorry. So number 7. So 7 is distribution. If you go into stats, that's for like the 1 variable calculations, the 2 variable calculations. We actually want distributions. I'm thinking about the wrong calculator here. So we go into distribution and choose which one we want. Just like binomial, because these are using inequalities, we're going to be using normal CD. In actual fact, for all of the kind of subjects or the kind of sections we're doing here, it's either going to be normal CD or inverse normal. We're not going to be using normal PD. I don't think I've ever really used normal PD, to be fair. So number 2, normal CD. We want a lower bound and upper bound. So the lower bound itself, we want to basically choose like in this case, we want it to be greater than 8. So our lower bound needs to be, because we want it greater than 8, we want to start at 8, and we want to go up to a really big number. So in this case, the rule of thumb, which I was saying about before, is just simply to times your standard deviation by 5 and add that on, which is not that big in this case. So I could just choose 9 as being the upper bound. So that's 5 lots of 0.2 is 1, 8 plus 1 is 9. If you want, and you really just don't want to even do that calculation, you can just whack in a big number there and it'll still do the same job. So I'll put 9 in for now though, just to show you. The standard deviation is 0.2 and the mean is 8. Press equals, and you can see here we've got 0.4999999, which is 0.5. If I just go back and change this bottom bound just to being really big, you'll see that this time it is 0.5. So the rule of thumb is 5 standard deviations to get pretty much spot on. If you just whack in a big number, it will also work. For that second part, I'm just going to put in 7.8 and 8.2. So 7.8 is lower and 8.2 is the upper. Everything else stays the same. And we get 0.682689 blah, which is 0.68. So you can see how that works on your calculator. Just going to pause for a second just to get up a slightly harder question. And so we've got question 8 here. The percentages or percentage scores of group of students in a test S are modeled as normal distribution with mean 45 and standard deviation 15. The first thing I'm going to do is write down what that is using basically our modeling notation. So we know that X, or S in this case, so S is modeled normally, normal distribution with mean 45 and standard deviation 15. So it's going to be 15 squared. So getting used to that is quite nice to start with. Find the probability that S is bigger than 45. Well, 45 is the mean. Bigger than that is going to be 50%. Part B, in between 30 and 60. Well, 30 is 15 less than 45. 60 is 15 more. So again, this is that second, that one standard deviation each side. So apologies. So we've got P of 30S and 60. That's one standard deviation each side. That's going to be 0.68. And finally, C, 15 is 30 less than that, which is 2 standard deviations less. So the probability of 15 less than S less than 75. It's the worst inequality ever. You'll notice that this is 30 above and 30 below where we're starting. So 45, if we take away 30, we get 15, and add 30, we get that. So this is basically 2 standard deviations above and 2 standard deviations below. So for this one, it's going to be 95, so 0.95. And again, I'm just using these particular rules up here. So 1 standard deviation, 2 and 3. So I'm not using my calculator for that. That's going to be in the next section. Part D, Alexia states that since it is impossible to score above 100%, that this model is not suitable. State with a reason whether she is correct or not. So for this particular one, it's kind of makes you start thinking, oh, is she right? Is she not right? And it's quite hard to know kind of what's going on here, but this model is quite good because even though it is impossible to get above 100%, at that point, those percentages become so small. So let me just show you on the calculator what's going to happen here. So let's say we want to go above 100. So lower bound 100, and then upper bound, let's just go really big, see what the percentage is for everything. Mean is 45 and standard deviation, wrong way around. Standard deviation 15 and mean 45. So this is everything above 100, like 0.000012286. That's tiny. We're talking such a small percentage being included there. So it's not unreasonable for this. Let's just have a think about where 100 is as well. So we've got a mean of 45. How do you get from 45 to 100? Well, we need to add on there 55. And 55 is actually only 3 and a bit from the mean. It's not even 5 above the mean. So it's kind of looking at where we're at there. It is quite a reasonable model. These percentages are quite small, so it is suitable. You could say you can't score less than 0 either and do the same idea. So if I go back here, the lower bound we could put in as a really big negative, and then the upper bound put in a 0. And you can see there's a very small probability that we're less than 0. And of course, it's impossible to score less than 0 as well. But it's just looking at what's actually on there. So yeah, hopefully that makes sense. So and we'll go on to the next bit, which is purely using the calculator. So the next little bit is finding probabilities using the normal distribution. So this is using the calculator and purely using the calculator, to be fair. So part kind of 3.2 or chapter 3, part 2, I actually think is quite straightforward. I've got a basic question and a little bit more kind of in depth, just talking through how to actually do it. So X is modeled normally. I'm going to put down what these are just next to it. So we've got mean is 30 and standard deviation is 4. We want to know when X is less than 33. So if it's less than 33, we know 33 is the upper bound. 5 times 4 is 20. So we need the lower bound to be at least 13 or less. I'm actually just going to put 0 in and put 33. Do not get used to just putting 0 here though, because some things can have a negative. Just make sure you're at least 5 standard deviations away from that mean. This is 4 and this is 30. And just press equals. So we got 77% or 0.77. So for part A, probability that X is less than 33 is 0.7733. Part B, the probability of X being greater than or equal to 24. So notice we can't really use the standard deviations for this as easily because it's not exactly a multiple of this. We've gone outside of that. So it's no longer just looking at multiples of the standard deviation. So this is why we're using a calculator. And before the calculators, we used to use lookup tables, and they're still given to you, but we're going to use a calculator. So if you are interested in seeing how you'd actually do that, let me know, and I can go through that at some point. So going back to this, the lower bound is 24, and we just want to go to upper bound here. So going for the upper bound, again, we want to do 5 times 4, which is 20. So we want at least 44 in our calculator, and just seeing what that comes out to be. Now, in this distribution, it doesn't matter whether you've got less than or equal to, greater than or greater than or equal to. They're all really interchangeable, because when it comes to a normal distribution, because it's continuous and we're dealing with like error intervals, the probability of being exactly a number is actually classed as being 0 in this distribution. So it's a little bit of a strange one, but all of these signs are interchangeable. It's not like binomial where you've got to be careful. Greater than or equal to, there's no difference in what you'd put in your calculator. So for this, I'm just going to put in like 65, because I know it's way above. Everything else is the same. So I've got 0.9332. And then C, we've got in between. So this is even nicer, because you've been given your bounds here. So we've got 33.5 and 38.2 as equals. I will put it down because we should. So I'm struggling to write here. 0.1706. And lastly, D, we've got an or here. So remember, in probability, we want 2 things. We've got, actually, we could do something a bit clever here. So we could work these out, and remember that or means plus. So we'd work this one out and we'd add it to this one. Or if we think about what's happening here, let's just draw that in. We've got the mean right in 30, which is here. This is down here at 27, and we want it to be less than. So we've got this bit. And we've got 32 up here. So a little bit closer, and we've got this bit. This is the same as doing 1 minus whatever's in between here. So we could do 1 minus the probability that X is between these 2 numbers instead. So we could have 27 and in between 32. So we could get rid of this middle bit instead. So you could work out these 2 individually, or you could work out that and then just subtract 1 from it, which I think I'm going to do here. I think I'm going to do it this way, where we subtract. I will show you using the calculator, it's the same though. So probability that X is less than 27 or that X is bigger than 32 is the same as doing 1 minus, and then the probability that X is between 27 and 32. And then I'm just going to work this out on my calculator. So 1 minus 27 and 32. Oops, wrong number. Oh, I'm sure I'm pressing 2 there. There we go. So 0.464. That is my actual first answer for this, and I need to do 1 minus that. Now your calculator can store these. If you do store and then press A, it says store to A. So when you come back out of all of this, you could go back to here and you could do 1 minus A if you wish, and that'll do that subtraction. Or you can simply just work out this manually, or if you've written it all down, like you can simply just work that out. Just to show you that's the same, so I'm going back to number 7 into this mode again. My lower bound, if it's less than 27, I'm just going to put kind of like minus 100, 27 as the upper bound, standard deviation 4, and mean is 30. That tells me it's 0.2266. Just put that up here for now. And we're going to add to that if it's greater than 32. So just coming back to the low bound's 32, and then I'm going to put a massive number above it. 0.3085. Add these 2 together, you get 11, 14, 15, 2, 3, and then 5, 0 point, which is pretty much what we got here. It's just the rounding issues. So I need to take it a little bit further, and we'd avoid that round. But you can see that even if we added these, it would be okay. So it doesn't matter which way you do that, it would work either way. And then finally, bit more contextual now. So the amount of mineral water in a bottle produced by certain manufacturers modeled as this particular thing here. So we've got basically like a 500 milliliter water bottle. Now we know it can be 14 above, 14 below, and we're okay there, which pretty much sums up real life. Sometimes you buy a bottle of water and it's got slightly more in it. Sometimes it'll have slightly less in it. I've never actually checked them all, but generally these machines aren't perfect. Part A then is to find the probability you get more than 505 milliliters. And part 2 is to find the probability you get less. So let's just do A over here. So the probability that W is greater than 505, we just want to put that in. So bigger than 505 means that's the lower. We know 14 is the standard deviation, so times that by 5 is 70. So as long as we choose our upper bound of 570 or more, I'm going to do 600. Our standard deviation is 14, and our mean is 500. So we've got a 0.36, so 36% chance that we'll get 5 extra milliliters, fantastic, or more. So 0.3605. And part 2, what about if we want less than 490? So I've paid for 500, but what's the chance that I'm actually going to lose 10 milliliters or maybe even lose more than 10 milliliters? So this time I want a bigger one than, so my upper bound this time is going to be 490. And remember that 70, I need to take that away. So at least 430 or less, I'm going to put 400. And then, so that's my chance of getting less. So 0.2375. It's actually quite big, 24% chance that I'm going to get less than 500 milliliters, less than 490 actually. So that's quite a few milliliters that I'm missing out on. A sample of 4 bottles is taken. Find the probability that all of the bottles contain more than 490. So in this case, you need to think back to your standard kind of probability question. In our standard probability question, just thinking about how we'd actually answer that. If you know the probability of getting less than 490, then you also know the probability of getting more than 490. And that's what we're looking at here. So let's just have a quick look at this one. So the probability of getting more than 490, let's just go part B. Is going to be equal to 1 minus this, which is 0.7625. So that's probably getting more than 490. Now we want to use that in order to find all 4 of them have that same kind of thing. So for each of these to happen, each bottle's independent. So I want sample of 4. So I want to check what's the probability of 1, then what's the probability of the next, and then next, and then next. Sorry if that's just flickering there. Okay, so the probability of 1 bottle is 0.7625. The probability of 2 bottles, we want to basically remember its probability of it happening. So I'm just going to click tick, another one happening, and another one, and another one. So remember in probability, when you've got and, it needs to multiply. So it's going to be this times itself 4 times. So in other words, to do this 4 times, it's going to be 0.7625 to the power of 4. So what I'm going to do is one kind of, I think on here, it should, remember that's my ounce. Yeah, so 1 minus that ounce gives me what I'm looking for here. And then I'm going to do that to the power of 4, which is 0.33798, blah, blah, blah. So 0.3380 if I round that to 4dp. But notice that all of my answers I've been doing to 4 decimal places. It's really just standard practice in normal distribution to do 4 decimal places. And all of the tables and things that we use are also 4dp as well. I'm not actually sure off the top of my head why that actually is, other than the fact of accuracy, because some of these numbers are quite similar. But it is always 4dp for this. I know we're used to using 3SF, but in normal distribution, we're always going to use 4dp. So hopefully this helps for the first little bit. I'll get some more stuff out shortly on the next few sections of this chapter. Thank you very much.